All right, it looks like we've got a couple people coming in, so maybe let's start in 1 or 2 minutes.
Okay.
Will I be able to drop you down to a part, is it part or attendee, or? I think you're muted.
Sorry. I think I may have to drop you down to the link.
Okay. Is that just in the Google Doc then?
Yeah, so when you get to that part of your intro, I'll just drop you down, and if you want to grab that link from your doc, then you can put it in the.
Maybe I should reload it.
All right, you guys ready?
I just need to make sure I have that link because I wasn't seeing it before. Yeah, I don't see it on my end, but.
It's on the first page under the jot form part.
Oh, okay.
Right there. Yeah.
Okay. Okay. Sorry.
No problem.
All right. Good morning, everybody, and welcome. I'm Coral Messig. I'm a 1L at University of Oregon Law. Welcome to the Public Interest Environmental Law Conference. For everyone, for coming to our panel offering a scientific critique of offset-dependent climate source solutions. My name is Coral once again, and this is Gabby, and we will be moderating this panel. I just have a few announcements, and then we'll get started with the panel. Don't worry, if you can't see yourself, this is a Zoom webinar, so all the attendees are automatically muted with videos off, so you will only be able to see the panelists. Throughout the panel, if you have questions, please use the Q&A function rather than the chat function. All of our panelists will be giving their presentations, and then there will be a 15-minute Q&A session at the end where the panelists will answer your questions. Please remember to be courteous of all viewpoints throughout the presentation and Q&A session. Additionally, if there are any legal professionals in the audience wanting to earn CLE credits for this panel, here's the link to register and pay on Jotform if you haven't registered to do so.
Okay, so Coral's going to become an attendee for a second and put that link in the chat for you guys in case you'd like to donate. I'll give her a minute to do that. All right, there we go. Let's get her back.
Am I all back now? All right, beautiful. Also, our alumni board, Friends of Land, Air, and Water, helps to provide stipends for students doing unpaid public interest environmental law internships. If you're interested in making a donation to help provide students with those stipends, information to do so will be on a Google document, which will be dropped the link in the chat below. Lastly, the University of Oregon is located on Kalapuya Ilhai, the traditional indigenous homeland of the Kalapuya people. Following treaties between 1851 and 1855, Kalapuya people were dispossessed of their indigenous homelands by the United States government and forcibly removed to the coast reservations in Western Oregon. Today, descendants are citizens of the Confederated Tribes of Grand Ronde Community of Oregon and the Confederated Tribes of Silts Indians of Oregon, and continue to make important contributions to their communities at UO. And across the land, we now refer to as Oregon. PILC would also like to acknowledge the traditional homelands of the Kalapuya peoples in the Willamette Valley and express our respect for the tribal nations of Oregon. We will now introduce you to our panelists. James Dyke is an academic writer and author. He is an associate professor in Earth System Science and assistant director of the Global Systems Institute at the University of Exeter, a fellow of the Royal Society of Arts, a fellow of the European Geosciences Union, and serves on the editorial board of the journal Earth Systems Dynamics. James is a regular contributor to UK and international media that includes BBC Radio and TV. Anders Carlson has studied climate change and its impacts for over 20 years. He earned a BA in geology and in German from Augustana College, Illinois, an MS in geology at the University of Wisconsin-Madison, and a PhD in geology with a minor in oceanography from Oregon State University. As an academic researcher and professor, Anders focused on ice sheet and glacier changes, their attendant impacts on sea level and climate, abrupt climate change, and the role of greenhouse gases and Earth's orbit in driving regional to global climate change. This passion predominates over into or translates over into his free time, where glaciers hold a special place in his heart, and he spends as much time as possible with his family exploring and skiing the alpine zone.
All right, so James is going to talk first. So James, if you want to get started, that'd be great.
Okay, well, many thanks, and many thanks for inviting me, and many thanks for that very nice introduction, which makes me sound much more impressive than I am. So I hope I don't disappoint. So I'm going to talk for about 20 minutes, hopefully a little bit less, on something called what I call net zero facts, theory, and wishful thinking. Does the slide look okay? Title slide. So one way to understand this talk is going to be a very brief introduction of what net zero is. 10 years ago, we wouldn't have been talking about net zero. Nobody really heard about it. But certainly in the last 5 years, it's come to dominate the discourse on climate change. And now it's all about net zero by 2050 or net zero by 2040. So where's net zero come from? And maybe what are some of the dangerous assumptions that lurk within mainstream climate policy? Well, this is what we already know. These are global greenhouse gas emissions. They're currently in the order of about 30, 40, more like billion tons of carbon dioxide that we pump into the Earth's atmosphere every year. You can see it's a very robust trend. The dissolution of the Soviet Union, the global financial crisis, COVID-19, perhaps the terrible events unfolding in Ukraine and Eastern Europe at the moment might put another dent in this, but thus far, nothing has really slowed the increase of greenhouse gas emissions, and consequently, concentrations of carbon dioxide in the Earth's atmosphere, as measured here in concentrations of parts per million, have been rising inexorably. Human-caused climate change, anthropogenic climate change, will continue until we get emissions to zero. That is our job today. We've got to take 40 billion tons of CO2 emissions and get it to zero. And until we do that, temperatures are going to continue to increase. Almost all of those emissions are coming from our use of fossil fuels, coal, oil, and gas. Yes, important land use change, agriculture deforestation, these kind of processes put carbon dioxide, but largely it's the burning of coal, oil and gas, which is pumping up concentrations of CO2. It is still the case that fossil fuels produce 80% of all of humanity's energy requirements. And that's even the case with this exponential deployment of wind, wave, solar, in particular solar power. The reason it's still about 80%, about the same percentage it was 10 years ago, is because humanity's appetite for energy is increasing just as fast. We need to turn the tap off. Somehow we need to stop burning coal, oil and gas, despite what many people will tell you, and maybe something that we might be touching on later in this talk. Now, that's going to be very challenging because if we're going to, let's say, get to net zero by 2050, that's going to be too soon, apparently, for sectors such as aviation and cement manufacturing. There are no credible plans for the electrification of wide-scale passenger aviation. There just aren't. Electric aircraft aren't going to happen. The aviation sector is putting most of its efforts in biofuels. Similarly, cement manufacturing and other things such as iron or steel production, you could see there are low or even zero carbon possibilities emerging, but at the scale at which they're needed, it's probably going to be the case that we are still going to be emitting carbon dioxide from some sectors by the middle of this century. So this starts us thinking about, well, what is net zero? And it begins with carbon neutrality. If by 2050, we've removed fossil fuels from almost everything apart from places like aviation and cement manufacturing, then we're going to have to remove exactly the same amount of carbon. So every ton of carbon we put in the air because of burning kerosene to get on a plane, we need to somehow remove a ton of carbon from the air. And as long as it equals out, as long as you get to neutral carbon emissions, then everything's going to be okay. So this is the idea of net zero. It's not absolute zero. There is no plans to completely stop emissions of carbon dioxide. The plan is essentially to ensure that every ton that gets emitted somehow gets offset or removed in some way. Now, this is meant to be a science-based policy, which kind of proceeds on the basis of the Paris Agreement. Science told us how much carbon we can burn if we want to limit warming to a certain amount. Also, science can tell us what are the impacts of such amounts of warming. For example, the amount of sea level rise we might see, increasing intensity of heat waves, increasing powerful storms, for example. And by 2015, the international community, society, politicians, wider society, determined that what constitutes dangerous climate change is about 1.5 degrees Celsius. Since pre-industrial periods, or since the start of the middle of the 19th century, we've probably warmed by about 1.1 or 1.2 already. So we are getting perilously close to 1.5. Now, recently, in fact, it was Monday this week, the Intergovernmental Panel on Climate Change released its latest landmark report. You probably did miss it in the news because there's been a few other things that have been taking our attention this week. But this is a vital piece of information. You can find it at this link listed below. And what this does is follows on from the Working Group 1, the physical basis of climate change report that was published last year. And this begins to unpack why should we care about climate change? What are the impacts? How might we be able to adapt to climate change, which is coming? And if we can't, where are the kind of vulnerabilities that we may see? There's a lot in the 3,964 pages of this document. Even the summary for policymakers, I think, is about 34 pages long. I just want to highlight a couple of things. The first one is that when we're thinking about impacts to risk to terrestrial and freshwater systems on the left and impact and risk to ocean ecosystems on the right, the difference between 1.5 and 2 degrees Celsius isn't arbitrary, isn't small. It can be everything. For certain systems, for example, warm water corals, it means extinction. We're not going to have any warm water corals at 2 degrees Celsius. We're looking at probably about 99% extirpation across all of the seas. We're looking at increasing loss of biodiversity change, structural change in ecosystems, widespread tree die-off, certain ecosystems producing carbon rather than sequestering it. And then on top of that, we're looking at the significant and large-scale disruption of social, political, economic systems, which are all ultimately embedded in the living world. These are not small differences. We've got everything to play for between 1.5 and 2 degrees Celsius. Of course, beyond that, we've got maybe civilization itself. It's still not impossible that we could be unlucky with climate sensitivity, or maybe very reckless and warm warm the Earth's climate by 4 or maybe even 5 degrees Celsius by the end of this century, at which point then I really do think you'll be looking at the large-scale collapse of civilization as we understand it. Significant regions of the tropics will become uninhabitable. Whatever left is humanity will be living in the higher latitudes, Canada or maybe Northern Europe. So we have still a tremendous amount of work to do. Now, when you look at 1.5, what does that work look like? It means that if we're going to limit the amount of carbon, so we limit warming to no more than 1.5 degrees Celsius, if we start about now, we have monumental mitigation rates. Monumental, probably above 10%. At the peak of the COVID lockdowns that we saw, global emissions reduced from the order of about 7%, maybe 8% at the peak. So we need to be looking at that and some for decades, pretty much over the rest of this century. So many people have concluded that since such steep mitigation is possible, the only way to achieve this budget is with very large negative emissions pulling CO2 out of the atmosphere. So look, it's impossible. It's being judged to be impossible. And of course, this is an example of policy-based science. We like to think that we have science-based policy, that scientists are informing policymakers onto what they can do, what they can't do, but the road runs in both directions. Policymakers are telling scientists, essentially telling academia, what is and what is not policy relevant. In the context of climate change, and let's say 1.5 degrees Celsius, this gets translated into how we are exploring potential future worlds. So on the left here, message, image, remind, GCAM, AIM, and WICH are integrated assessment models, which are very complex econometric models, which try to understand how may we be able to decarbonize our global society. Now, the thing to bear in mind here is on the right-hand side, you've got the different kind of warmings that will give you by the end of this century. It could be well under 2 degrees Celsius, which is Paris compliant. It could be above and beyond 5 degrees Celsius, which is basically our annihilation. If we're thinking about 2 degrees or maybe even 2 to 3 degrees Celsius, then these scenarios are assuming a significant amount of net negative. Basically, see the origin here? We're looking at zero, not just zero, but negative emissions. We're removing tens, potentially many tens of billions of tons of carbon dioxide from the air every year, starting around maybe the middle of this century till the end of this century and well beyond, because we've got to drag the system back down. If you look at the IPCC Assessment 6 Working Group report that was published last year, it is now giving us the very best estimate is essentially an overshoot assessment. So SSP 1 to 1.9, this is the long-term scenario that we think has got the best chance of keeping temperatures to no more than 1.5. But you can see in the midterm, around the middle of the century, it's going to overshoot. Other scenarios, arguably much more realistic scenarios, overshoot more and have higher, longer-term temperatures. If you were to ask climate scientists, where do we think we're going in terms of warming by the end of this century, I will not find any that think it's going to be 1.5. We're probably heading more towards 3 degrees Celsius. So how are we going to do this? How are we going to remove these billions of tons? Well, it's a process called carbon capture and storage. It's not a new idea. This is a capture of the carbon capture storage report from 2020. You can go, if you just Google that, you'll find the commercial facilities in operation. You'll find their capacity. It's very hard to actually identify how much carbon is currently being sequestered. And you'll discover this is not a new idea. For 50 years we've been going now, capturing carbon dioxide and then pumping it underground, first developed commercially in the Tyrrell natural gas processing plant in the United States, 1972. But you'll find that almost all of these facilities are something called enhanced oil recovery. They're not to take the carbon out of the air and to hide it in the Earth's lithosphere or crust. It's basically to get more oil out of the ground. And it's a process which in principle is simple. You might have a coal-fired power station, which is going to emit carbon dioxide as you burn the coal. You then capture the CO2, you're going to scrub the carbon dioxide out of the flue gases. Then that CO2 you concentrate and pump down into the ground. And what you do, you pump up a depleted reservoir of oil. So you're pushing up into the oil well. So there are clear commercial incentives to develop this technology. And in fact, this is what the technology has been developed for over the past 50 years. But of course, how that process runs could mean that you're going to actually emit much more carbon dioxide than you would ever store, because oil is being pumped up to the surface in order to be used, for example, in transport fuels, and therefore burn, and the carbon dioxide is going to get released. So really, whenever you hear CCS, you should think of CCUS. It's not carbon capture storage. So basically, there's very little storage. There's practically none. It's all utilization, and there are clear commercial motivations for that. But if we're going to undertake a process of removing, let's say, on the order of about 10 billion tons of carbon dioxide from the Earth's atmosphere each year for decades, then how are we going to do that? Well, about 5 years ago, BECCS was the answer: bioenergy carbon capture and storage. In principle, it's pretty simple. You've got a coal-fired power station. Don't burn coal in it, burn trees. You take the trees and turn them into wood pellets. You burn that, you're going to produce electricity. That's good. So that's carbon neutral. But you make it carbon negative by capturing the carbon dioxide, just like you did in the previous example from the flue, and then storing it and not using it for enhanced soil recovery, but basically just keeping it in the rocks. Now, because trees absorb carbon dioxide as they grow, if we run this process for decades, it will reduce concentrations of carbon dioxide in the Earth's atmosphere at the same time as produce large amounts of electricity. And what's not to love? Unfortunately, it's already proven to be a disaster. There's mounting evidence that it's accelerating the deforestation of old growth forests in Europe, in South America, and it's becoming clear that the hopes and prayers associated with BECCS are not going to be realized. Consequently, there's a new game in town. This one is called direct carbon capture, or direct air capture, DAC. Climeworks made some international headlines around about September, I think it was, because this is a facility based in Iceland, which is now the first large-scale application of direct air capture. How does it work? Well, basically, these are kind of large-scale sort of air conditioning systems. They kind of suck in the air, and what they do, they separate out all those molecules of carbon dioxide, and then they store that underground. Why is Iceland an interesting place to do that? Well, it's geologically active, and basically one of the challenges we've got for carbon capture and storage is that you need to mineralize the carbon dioxide. No good pumping it down to the ground only for it to leak back up again. You've got to get that carbon dioxide into some kind of mineral, a kind of like a limestone. And the geology in Iceland is very warm, very active. Basically, you can accelerate that process. The demonstrator project is hoped to be able to capture and sequester on the order of 4,000 tons of carbon dioxide each and every year. And just to remind ourselves, current emissions are 40 billion tons of carbon dioxide. So there is a vast scale in terms of operation between this very pilot facility and what carbon capture and storage is supposed to be doing within the next couple of decades. Now, I talked about the fact that it's no good just putting the carbon dioxide in the ground. You've got to kind of sequester it. And there's already mounting evidence that that's not going to be easy, or certainly not as easy as many of the advocates for this technology have proposed. So if we look at the Gorgon carbon dioxide injection project in Australia, it's been running since, since 2019, but it hasn't really been doing much until, let's say, the last 2 years or so. It separates carbon dioxide, which gets emitted through natural gas processing. And the idea is that whilst it might then sell that natural gas, which gets burnt and the carbon dioxide gets emitted, the CO2, which arises through that separation process, they're going to store in a dedicated geological storage. Well, it doesn't work very well. One of the reasons it doesn't work very well is the great challenge of carbon dioxide sequestration is geological. So there are two main problems we've got scaling up carbon capture. First is the mechanism by which we capture it from the Earth's atmosphere. And the second is where to put it. One of the challenges we've got as we scale up the number of sequestration projects, each and every one of those projects may have its own particular geology that we're going to have to fix. Doesn't mean it's impossible, doesn't mean we can't do it, but it could mean that the very wild optimism that we've had, certainly from some industrial sectors, that this thing could just scale up, like, for example, the deployment of solar panels, could be very, very reckless. So I'll finish with some ways forward. Net zero is a really important framing, and net zero is here to stay. The challenge we've got is that some net zero proposals are essential greenwashing. What we need to do is to ensure that when an organization or a company or some kind of entity comes up with a net zero policy, we have clear what your actual mitigation targets, what you're going to do in terms of stop burning coal, oil and gas, and then anything outstanding, how much you're proposing to remove. We also need to level with the public. Net zero actually means net negative. We need to build vast machines. We need to develop entire industries and technologies, and we need to deploy them at scale within decades. And we do not have any idea how to do that. Doesn't mean it's impossible, but this is going to be a massive amount of funding. And it does mean younger generations and people who have yet to exist actually are going to be burdened with a significant economic and energetic debt. It's going to require billions, if not trillions, to build, and many, many gigawatts of electricity to run. The third one is that we must base proposed removals on our robust science. At the moment, the amount of carbon that we need to remove is based entirely on how slowly we think we're going to mitigate. They're almost been invented as ways to balance the books. We need to have very robust science and say, this is what the science says we can do now. This is what it's going to be in 5 years' time. This is what it'll be in 10 years' time, and not allow any policy which exceeds these removals ability. And the last one, and this is a bit of a plea to academics, my fellow academics, is I think we need to empower academics to produce change and break out of some of the policy-based strictures that have been in place. Many of the academics that work on integrated assessment models that produce 1.5 scenarios will be completely skeptical as the feasibility of those scenarios. I haven't met one. I haven't met a single person who works on integrated assessment model that thinks we're anywhere near to limiting warming to no more than 1.5. And most of them would agree we need radical action. But that radical action is never going to happen by producing yet another report, which is further demonstrating we are moving ever nearer to the precipice. So we need to get academics to step over the line, become much more engaged. And here I end with a plug. This is an organization I've been working with, helped create. It's called Faculty for a Future. Visit facultyforafuture.org and find out how you can, as an academic or somebody interested in academia, can help accelerate the transition to a more sustainable, resilient and fairer society. At the moment, I don't think academia is doing its job. I don't think it's fit for purpose in many instances. There's an awful lot more that we should be doing. And there I will end it. Thank you very much.
Okay. So should I take over then? Okay, great. Share. Is that working for everyone? Okay, great.
Looks good.
Thank you. All right, great. Thanks, James. Yeah, so that's my talk here will very nicely build off of what James just talked about. And I want to look at it from an impact side of what net zero means for the future and where the science is now on what we need to do. So I'm looking at carbon emissions here and what we've already committed to climate system to from what we've already emitted, and how these ideas of net zero and negative emissions play into that. And as my bio introduced me as, I really love ice, and there's a picture of the Greenland ice sheet here, which we've probably already doomed with even our current level of emissions. I'll come to in a second. So first off, let's look at like this idea of policy, as James talked about, driving science. And this is a graph here from the paper that came out last year, Huna et al. On Nature Climate Change, that's showing you projected warming by 2100 here on this thermometer, and then where from integrated assessment models, as he was talking about, where these different current policies combine together, nationally determined contributions from the Paris Accords, and then also net zero come into play, and where the Earth is going to at our best level right now. And let's focus in on this blue bar here, which is from this study, how they put together these different emission scenarios and emission targets. And the dark line here is the median of what the warming will be. And so based on global policies from all the different countries, we're on track to right now warm close to 3 degrees C by the end of the century. And then if you include then the Paris Accord national determined contributions, this number comes down a bit, so maybe 2.5 degrees C, and then within the range, you can see we could still be up to 3 degrees C. But even with the Paris Accords included, we're still above 2 degrees C to up to 3 degrees C of global warming. And that doesn't play too well. And so with a spate of new net zero pledges coming from a lot of different countries, you include this later sequestration, pulling down a carbon offsets into these issues, you then can bring this line down to 2 degrees C. And so all of a sudden policy forces combined a bit with some scientific inquiry brings down future climate change to something that seems palatable. Oh, we've already, with these net zero targets, we can now hit 2 degrees C. But that's right. But how are we going to do it? And that's the real question. And it's a paper here by Huna included whether countries will follow such a strategy is unknown, as countries generally have not specified how they plan to achieve net zero targets. This is basically me saying, I'm a billionaire. I don't have $1 billion now. I may in the future, but I can claim I'm a billionaire. And that's kind of where we're at. So it's looking at these here, and well, how are they supposed to achieve net zero? And James went into more detail on this. I just want to talk a little bit about these different methods. And one is carbon capture and storage. And the economics and the how to actually employ this, as he went over. I want to just look at it from how will this impact us in going forward in climate change? And future carbon capture and storage is really just kind of what Wimpy used to say in the Popeye comics. I'll gladly pay you Tuesday for a hamburger today, or I'm gladly will sequester carbon in the future by some means if I'm allowed to emit it today and continue into the future. And this is really just passing the buck. We've already done this before, back in the 90s with using cost-benefit models, integrated assessment models like the DICE model, that said it's too expensive to deal with climate change now, but there'll be so much more money in the future by not dealing with it now that they can deal with it in the future. Well, that's not coming to reality, and we're having to deal with climate change now, and we don't have any more money. So it's just another example of passing on the buck. And we can move now a little bit further here and look at this review that came of net zero pledges and describe these here. This is another paper came out last year, reviewing net zero pledges so far. And it said governance, accountability, and reporting mechanisms are currently inadequate. Long-term ambition is often not backed up by sufficient near-term action. Many entities have not yet set out detailed plans to achieve their pledges and are opaque about the role of carbon offsets in place of cutting their own emissions. The environmental and social integrity of some of these offsets is questionable. As a result, some advocates have accused these pledges of amounting to a little more than greenwashing. And so this is countries greenwashing. This is not ExxonMobil having a net zero pledge in greenwashing. This is our policymakers are making our bad policies right now seem a little more palatable to us and like there's something happening, but that's not the case. So I come here back to these carbon offsets, which is not carbon capture and storage, which is actually bringing CO2 out of the atmosphere. This is ways that companies, individuals, and countries have tried to offset their current carbon emissions. And many times this doesn't actually pulling CO2 out of the atmosphere. Many of these offsets, and this could be you feeling bad about taking an airplane flight across the country and you buy some carbon offsets to defray your emissions from flying from, say, Oregon to New York City. What you're really investing in is investments in wind and solar farms and building some kind of wind and solar infrastructure. And this is occurring while your one is still burning fossil fuels. So there's no offset. It's rather, I'm going to invest in a green technology while I'm still actually doing the bad thing here and emitting carbon dioxide. So there's no actual reduction in CO2. And it's not clear if these wind and solar farms that you could be investing in are actually going to result in the closure of a natural gas plant that would then reduce CO2 emissions. So there's actually not an offset. It's unclear. And, are these things ever really built is another good question. And another offset one sees is not cutting down forests. And this is basically double counting. And so forests are a carbon sink. But by saying I'm not going to cut down the forest, you're double counting that sink because that's already in the carbon budgets. The CO2 that your forests here in Oregon are sequestering is already accounted for in those graphs of our global carbon budget. And then by not cutting it down and saying that will offset my future emissions is not correct. That's double counting this sink. And Putin's in the news a lot today, but last year he claimed all the forests of Siberia. By not cutting them down, that's their carbon sink, so they can continue to emit CO2. So it's double counting a sink that's already in the system. And here's the point I want to come back to now. Despite all the major impediments to bringing about carbon capture and storage, we desperately need it. But this is where we have to break apart the net zero thing here. One, we need to cut our greenhouse gas emissions now. We have to stop emitting CO2, and we have to do that because it will cause future global warming. But we also need to independently start drawing down CO2 in the atmosphere because we already have too much CO2 in the atmosphere. 1.5 C is put forward as dangerous, but where we're at right now, 1.2 C is also dangerous. 1.5 C is just more dangerous. We're already in the critical zone and we have too much CO2 in the atmosphere. And that's what I'm going to focus on the rest here, why we need to do this. So we need to reduce our emissions immediately. And so we do need carbon capture and storage to deal with already the CO2 we have emitted. So we can't put any more out there or we're going to make things worse. And we already have committed the crime. So we have to pay the time and actually now go back and pull the CO2 out. And we can do that by carbon capture and storage. And another way is we need to bring about new forests, reforestation, and new grasslands, growing back grasslands, which are our natural sinks. So not cutting down more trees and calling that not cutting, but I say not cutting down trees, but we rather need to grow the trees back that we've already cut down and grow the grasslands. And one study a couple of years ago estimated that we could absorb 20% of the US emissions alone by reforestation and regrowing of our grasslands. And so there are some ways forwards, and that's what we need to deal with what we've done. So here's how it works out. So this is a graph showing you from 1850 to 2025, so a little bit into the future. And then at the bottom here is our global carbon emissions since 1850 from the Global Carbon Project. Here's the resultant atmospheric CO2 concentration from ice cores in Antarctica. Then up here, the Mauna Loa record that started on Hawaii that Al Gore made everybody in the world aware of. And then up here is the most recent NASA Goddard Institute for Space Studies global temperature normalized to the 1880 to 1920 average. So you can think of this as temperature change since 1900. So we've already emitted 2,431 gigatons of CO2 as of 2020. So that's 2,431 billion tons of CO2. This has raised carbon dioxide levels now as of last year to 416 parts per million in the atmosphere. And these are levels we have not seen in over 3 million years. And so you think about it, 3 million years ago, our ancestor Lucy was living in Africa. So Australopithecus is the human equivalent that's developed and evolved to live in a 400 parts per million atmosphere. We are not. We evolved in the ice ages, and when CO2 never was above 300 parts per million in the atmosphere. So we're not evolutionarily made for this climate. And what has happened then is we've now warmed about 1.1 to 1.2 degrees C, depends on how many years you average, but the last 5 years here averaged to about 1.2 degrees C of warming since 1900. And I want to point out that this temperature is just too hot. Why is this bad? Well, we talk about these temperature targets, but we have to think about the heat we are trapping in the earth. And the earth is like an oven. And by increasing CO2, we're just holding in more heat. And so the CO2 is kind of like turning up the thermostat, and we're sitting in there cooking. And right now, we have added 358 zettajoules of energy to the Earth's atmosphere that's extra. This is how much energy our oven is warmed up. And a zettajoule is 10 to the 21st joules. And so you got to remember, a joule is also a calorie. So this is built up in the atmosphere. And this is a paper that came out 2 years ago, but was targeted for the Working Group 1 IPCC report that came out last year. And so this is showing you where this accumulated energy here, and the vast majority of it's gone into the oceans. And that'll show you here in this next graph here. So this is where this extra energy has gone, and it's this is accumulation since the early 1960s, when we first started to have ships going around the oceans and actually measuring the heat content of the ocean. And so the blue lines here, the ocean absorbed energy here. Then the dark line, the brown line here is the energy has gone into the Earth's surface, into the ice, sea ice, glaciers, and ice sheets. And then this little purple bit, that's what's left over to warm the atmosphere. So we have a lot of energy that's been trapped on Earth that's moving around already that we need to get rid of. And to do that, we have to turn the temperature down on the oven. And to do that, we have to lower CO2 in the atmosphere so this heat can dissipate back out into outer space. And to do that, the best estimates are we need to get back to at least below 350 parts per million CO2 in the atmosphere, which we crossed in 1988. And if I was 11 years old when we crossed that, and things started to get wonky in the 90s and they continued to get worse in the 80s. Things still seemed pretty good. We had snowy winters and so on. So you can almost see a correlation in lifetime between what we were experiencing in that. And so to put this into perspective here, the 350 zettajoules, that's the same amount of energy as 1.3 trillion trips to the moon. So it's a lot of heat we have extra in the earth. And here's what it's doing and why we need to lower these CO2 levels. And we're here in Oregon. We experienced the worst heat wave on record last summer. And this is a figure here from the World Weather Attribution Service. And the people who led this study were Canadians. So you can see they've got Canada British Columbia here highlighted, and they cut off Eugene down here. But this is showing you the temperature, the temperature change from the warmest day on record relative to the heat wave. So this is not 5 degrees centigrade of warming relative to some average. This is 5 degrees C warming than the hottest day ever previously experienced. And that's what happened last summer here. All these red dots are 5 degrees warmer than the hottest day ever recorded in Portland, Vancouver, Seattle. And this heat wave is virtually impossible without human greenhouse gas emissions. And basically the earth is already too hot. So let's look at another example why this is happening. I'll come back to that 400 part per million threshold from 3 million years ago. And where we've trapped all this heat into the earth and it's going to start cooking us. We've just started to trap it. And so this will move to Ellesmere Island. We're going to fly up here to the high Arctic. This is in Arctic Canada, 80 degrees north. And this is what it looks like today on Ellesmere. And Ellesmere is barely ever gets above 0 degrees C, 32 degrees Fahrenheit in the summers. And so it's always frozen. But 3 million years ago, the last time CO2 was above 400 parts per million, Ellesmere Island looked like this. There are beavers living there. There were little proto horses, black bears. And that's 3 million years ago. And so this is what they think it looked like. And this looks similar to what Labrador does like today. So down here in further south in Canada, very north to us here in the lower 48. But this is not that. This is not glaciers and ice sheets. This is, 60 degrees in the summer and you call that a warm day. And so what this is doing is when the earth adjusts to this extra heat we have, Ellesmere is going to go from like this to like this. And so the earth is already too hot and we're going to start to adjust to these climates we saw in the past. And this is occurring now. There's a paper from just 4 or 5 years ago, but tundra be damned. The beavers are actually moving back into the tundra because the climate's too warm. And now we may think like, oh, they have a greater habitat range, but that's not the case. This is not where they're supposed to be, how the earth is constructed these days. And these new beaver ponds are thawing permafrost and releasing more methane into the atmosphere. So the biology is responding already to this higher CO2, and it's making positive feedbacks that are only going to make things worse. So why is this occurring? And that's because time scale matters. And so I'm a geologist who's now moving into addressing issues of climate change rather than just documenting the impacts. We think about things on different time scales from policymakers. And we have to remember that just because the graph stops at 2100 or 2050, Earth doesn't stop. So this is a figure showing you the response of the Earth system to a doubling of carbon dioxide in the atmosphere. So going from 280 parts per million during the pre-industrial to 560 parts per million, but doing this instantaneously in a model. And we will, if nothing happens, we'll definitely cross 560 this century. And so you double the CO2, the immediate feedback is the Earth immediately warms 1.2 degrees C. And so this is instantaneous warming, like immediately turning on a heat lamp. And then in the years, you have clouds, water vapor, snow, sea ice start to respond. The upper ocean heats up a bit. You have some changes in ozone, dust in the atmosphere, and then these slower things come into play. And so you've only done one bit. We immediately doubled CO2. And then over time, as we turned the temperature up on the oven instantaneously, now things start to cook. And the longer we stay at this elevated CO2, the more things cook. And down here, we start to destabilize the ice sheets. And so instantaneously we warm 1.2 degrees C. This is the number we usually hear about in the news. It's called Earth climate sensitivity, where after about 130, 40, 50 years, it's warmed by 2 to 4.5 degrees C. And this is what people have worried about. But then over a longer time period, when the Earth finally adjusts and we have beavers and forests on the shores of the Arctic Ocean, it's warmed by 3 to 6 degrees C. So there's a time scale matters. And here's what's we've already done. We've already given the ice sheets a 1-2 punch by going above 400 parts per million in the atmosphere. So we are at 1.2 degrees C of global warming, and we've already begun the deglaciation of Greenland and the marine portions of Antarctica. And this is because it only takes about 1 degree C of local warming on Greenland to get rid of that ice sheet. It just takes a long time. If it warms 2 or 3 degrees C, it'll happen faster, but we've already destabilized it. And the same is true for West Antarctica, for Antarctic ice sheets that are in the ocean. So like the large portions of the West Antarctic ice sheet and portions of the East Antarctica. All it takes to destabilize those is about 2 degrees C of local ocean warming. And this is based on models, but this is also based on geological observations and how high sea level was 3 million years ago and observations of where the ice sheets were then. Another thing has happened, and not the ice sheets, is we've already doomed at least 1/3 of the globe's glaciers to disappearing. So this is not the ice sheets, but Iceland, Oregon, Washington, Alaska, the Himalayas, Kilimanjaro, the Andes. We're going to be losing a lot of glaciers, and that'll have real problems for water resources in local communities. And so what we've already done now is kicked off this slow response of glaciers that can get worse, will get worse in the future as we continue to emit CO2 if we don't do anything about it. But even as of right now, by the end of this century, we've already contributed to about 1 inch per decade of sea level rise occurring in the next coming decades. And over time, these ice sheets will respond. And this is just what we've done now. If we ceased emitting CO2 tomorrow, this is already baked into cake. And that's why we need to continue to remove CO2 in addition to stopping emitting it. And so to reverse this ongoing process of the Earth being too warm already and the oven being turned up. So to close out here, the ice cube is out of the freezer. And so if you think about it, you take an ice cube out of their freezer, it is no longer stable. It will eventually turn into a puddle of water. It just takes a bit of time to do it. And the hotter your kitchen is, the quicker the ice cube melts. But we've already removed the ice cube from the freezer. So we need negative emissions now from carbon capture and storage, increasing our sinks to put the ice cube back in the freezer so we don't continue to bake the planet. We need to get CO2 levels back down to where we can release enough of this trapped heat back into space and stop these ongoing processes that we've already committed ourselves to by going to 416 parts per million in the atmosphere. So let's say, take the rosiest picture put forward by policymakers and these net zero pledges. At best, all they're doing is delaying putting the ice cube back into the freezer. And the longer it stays out, the more the Earth will adjust to this too hot a climate already. And so the glaciers and the ice sheets will be smaller, the tundra will have retreated, and all these things will be worse. And so net zero at best is keeping that ice cube out in the kitchen longer. And at worst, we're trusting politicians who pull us out of all these accords all the time and never follow through on all the Kyoto onto Paris. And, you know, like these things, you're looking at people who have political pressures to do other things. And so at worst, they're probably just going to leave the ice cube on the counter and it's going to melt. And so these net zero pledges are just saying, oh yeah, I'm going to put the ice cube back, but we never really do. And so we need to not only stop our emissions now, but we also need the negative emissions in addition to that. And so I'll just stop there. And yeah, thank you very much for your time.
Yeah, thank you, James and Anders. That was awesome. So we are running a little short on time. We do have a panel coming up right after us. So I'm going to sort through a couple of these questions here. We'll just start with the first one up top. I think, Anders, you touched on this a little bit when you were talking about the Arctic, but so Craig asks, can you identify what a net zero emissions would do to transportation, food systems, and delivery, national economies, and social structures? Can you project forward what life on this planet would be like? And that's a really big question. So I'll just ask each of you to maybe say one or two like really important and striking things that you think about that.
Who do you want to go first? Who do you want to solve humanity's challenges first?
James, let's have you go first real quick, and then we'll have it.
All right. Given the scale at which we need to decarbonize, the rate at which we need to do that, and ensure that people have good quality lives, I think it means there's a significant redistribution of resources, right? Anders spoke about this kind of cost optimization, and the argument has always been, don't decarbonize too fast because you're threatening future economic growth. Why should we care about future economic growth? Because that will allow poorer people to not be so poor. There's already sufficient wealth. There's already sufficient resources that nobody needs to go hungry or be, energy poor. The problem we've got is where the resources, where the wealth is concentrated, and it's increasingly concentrated in a smaller number of bank accounts. And it's still the case that it's largely driven by fossil fuels. 80% of humanity's energy is generated. Significant fraction of wealth is still generated by fossil fuels. So I think if you're thinking about the kind of decarbonisation, the transformations that we need to do that in time, then we must be talking about climate justice, which means thinking about how is wealth, how are resources distributed now, and then how can we make arguably a more equitable distribution.
Yeah, I completely agree with that. We have all the solutions, and it's just we have lacked the global willpower to do exactly that, redistribute the wealth and be equitable in how we plan for the future. You could almost say we need to move towards a Star Trek based lifestyle of no money and everybody helps everybody else out. And we try to do for the best for humanity, because we know that the air connects us all. And so the old saying of my rights end where your nose begins. Well, the problem is with the atmosphere, everybody is impacted by what we do. Our driving a car is impacting people in Africa. And so what kind of car we drive matters. And so we need to, the scale is huge. And so we need to have global leadership and it's got to come from a top down reordering of society, basically. But we have all the solutions. I mean, we just have to, we lack the willpower to go and make it happen.
Okay, that was great. Thank you, guys. So I am actually going to end us here so that we have enough time to start our next panel. But I do want to let everyone know we do have a question about access to the recordings of these presentations. And they will be posted to YouTube within the next couple days, within a few days of the end of our conference, which is on Sunday. So given that, I would like to thank our panelists and Coral for your good work today. And I'd like to also invite you guys to participate in any other panels. Go ahead and check out. We have a full program for the rest of the weekend through Sunday evening. So would love to see you around.
Well, many thanks so much. And well done, everyone. This looks like an amazing event.
Great.
All right. I'll end it there. Thank you.